Clara Löh, Regensburg, at uniform boundary conditions and simplicial volumes.
Thank you very much, and thank you for the invitation to this really nice institute. So yeah, I'll talk about the uniform boundary condition and simplicial volume. So I'll first introduce what the uniform boundary condition is and why one could be interested in that. And then I'll present a slightly different topological problem on simplicial volume, and then in the end I will talk about again about the uniform boundary condition and how it can be used to do something on the second part. So yeah, first let me just give the definition of the uniform boundary condition, and I think was first phrased in these terms by Matsumoto and Morita. So what's the setup we have? We have a normed chain complex. So let's C star 3A. Normed chain complex. So that means, well, it's a chain complex, and maybe in the simplest case it's just a chain complex of real vector spaces, and we have a norm on each of these chain modules, and the boundary maps are supposed to be continuous with respect to these norms. And then we are given a degree n and n, and so then this chain complex C star satisfies the uniform boundary condition in degree n if the following is satisfied. So whenever we have a chain that is in the image of the boundary map, so it's a boundary. So it's in the boundary map of from degree n plus 1 to degree n, so this sits in Cn. Then of course by definition we know that there is a chain B in Cn plus 1 such that the boundary of this chain is C. But now we can ask that this filling is somehow efficient, right? It's a cheap filling. So we want to have that the norm of B is at most some constant times the norm of C. So we ask for a global constant that makes this happen. So we are asking for a good filling, uniformly good filling of our chains. Okay, so well, okay, if you are into normed chain complexes, then this is like an obvious condition to look at, but maybe you're not, so I'll give some context where this appears more or less naturally. So let me talk about some applications. And the first one is in bounded cohomology. So we already learned about this in Roberto's talk. So we have the following theorem, again by Matsumoto and Morita. So let's assume that we have a group, gamma, and we are given some degree. Then we have the following. Namely, the first thing is that if we look at the chain complex of gamma, say with real coefficients, so this is just, okay, what do you take? You take the simplicial resolution of gamma, and then you take the gamma coinvariance of that. So this gives you like a standard chain complex associated with gamma, and this carries a norm, namely the L1 norm. And that's the norm that also Roberto already defined. So you just count how many simplices you have in your chain, and you weight it with the coefficients that you have in your chain. So that's a norm chain complex. And then we want to characterize whether this has NUBC or not. So this has NUBC if and only if. Well, also, as Roberto already explained, there is this comparison map from bounded cohomology of gamma to the ordinary cohomology, so you just forget that your chains have been bounded. And this is equivalent to this map being injective. So if you're interested in bounded cohomology, this is like a useful term. Okay, so that's one thing. And then we've already seen in Roberto's talk, you might also be interested in asking whether this thing is Banach or not. And so put it like that. So this thing is Banach if and only if. Well, now we don't look at this chain complex, but we look at the completion with respect to this norm. So take the L1 chain complex, that this has n UBC. Okay, so this, I mean, as I said, if you want to know some things about bounded cohomology, then this could be a way of attacking it. But of course, in general, this will be extremely hard because, I mean, you have to understand basically like all the fillings of your chains, which is hard. Okay, but you get something out of this because it's fairly easy to compute bounded cohomology of an amenable group, just by definition, because if you have an amenable group, what does it mean to be amenable? Well, you have an invariant mean on your group, and then you can just use this to define transfer to bounded cohomology of the trivial group, which is trivial. So as a consequence, you get that if gamma is amenable, then this chain complex has n UVC for every n in n, just because bounded cohomology of the of amenable groups is trivial. So that's one consequence of this, but well, maybe it's not so striking because it's all in terms of all these notions. So another thing which is maybe more interesting is a theorem by Sommer, and also Roberto talked a little bit about that. So what Sommer showed is the following. So the chain complex, if you look at the chain complex of the free group on two generators, and you look at the L1 completion, this does not satisfy two UVC. So this does not satisfy the uniform boundary condition in degree 2. So this means you have like small chains in this in degree 2 of this chain complex that are boundaries but cannot be filled easily. And in particular, we see that H3 bounded of the free group is not Banach. So the zero norm subspace is non-trivial. Okay, and also as we have seen in Roberto's talk, I mean, the arguments basically to prove this, they use three-manifold topology. Okay, so these are applications in bounded cohomology. Let me give you a different class of examples, namely for simplicial volume. So let me give the definition, and this goes back to Gromov. So let M be an oriented closed connected n-manifold, then simplicial volume of M is defined as follows, namely, well, let's denote it like that. What do we do? Well, we have this one norm on the singular chain complex, And then we have already seen, at least for classes in bounded cohomology, that you can associate a number to a class just by optimizing over all cycles in that class. And we will do that. And if you have a manifold, then there is a distinguished class, namely the fundamental class. So we just do that. So this is the infimum over, and let me make it very explicit, the sum of absolute values of the coefficients where the sum over aj sigma j in C and MR is a fundamental cycle of M. Right, so this is just optimizing the L1 norm of fundamental cycles. Okay, so this gives you some number. And let me maybe mention some key examples. And one of the examples also already occurred, at least implicitly, in Roberto's talk, namely, well, if M happens to be a hyperbolic manifold, closed hyperbolic manifold, then this thing is positive, and even better, we more or less know exactly what it is, namely, so if M is hyperbolic, then the simplicial volume of M is nothing but the volume of M, well, divided by some constant. It only depends on the dimension of M. And what is this constant? It's just the volume of an ideal regular simplex in Hn. So this is something that's very concrete geometrically, and it determines the simplicial volume. So this was first proved by Gromov and Thurston. And well, why is this interesting? Well, okay, one consequence of this is, if you believe this, is that, well, the simplicial volume, the way it's defined here, right, this is a topological invariant. It's invariant under homotopy equivalences because, well, is basically defined in terms of singular homology, which is a homotopy equivalent, homotopy invariant, and then you can easily see that also the norms of these classes will be invariant under homotopy equivalence. So this number here is homotopy invariant. Well, it's something that's not obvious for the hyperbolic volume. And of course, I mean, we immediately connect this with Mostow rigidity, and that's in fact where it first occurred, namely in Gromov's proof of Mostow rigidity, he used this fact to prove that the volume is of hyperbolic manifold is invariant.
Where does it break down in dimension 2 then? Dimension 2?
Well, you need other stuff in order to prove Mostow rigidity. I mean, there's this whole thing on the boundary going on. And
okay, but that result is...
I mean, this is always true.
Oh, okay.
This has nothing to do with dimensions. Yeah, this is always true. And more or less, I mean, so maybe the interesting direction is to see that this thing is non-zero, and we learned that basically in Roberto's talk, how to do that. Namely, if you have such a chain, well, let's assume that the sigmas are smooth, then we straighten them, so we have geodesic simplices, at least in the universal covering, and then we can use integration to prove that this will be bounded away from zero. So, and for the other direction, you need a concrete geometric construction. Okay, so that's that. And then, so this is like the case of negative curvature. And then at the other extreme, we have amenable fundamental groups. So if pi1 of M is amenable, then simplicial volume of M is 0, and this was proved by Gromov, and also a different proof was given by Ivanov. And of course, we have to assume that the dimension is non-zero, but yeah. Okay, so what does this tell us? So, I mean, which groups are amenable? For example, all abelian groups are amenable. The trivial group is amenable. So you have, whenever you have a simply connected manifold, this number will be 0, which is maybe more or less surprising because at least I don't know of a geometric proof to prove that. Okay, so that's the invariant that we want to look at. And so let's see, I mean, now you could start to calculate more examples and more examples, but sooner or later what you want is something like a gluing formula, right? So So in the simplest case, you want to have something like the following. So let's assume we have two manifolds with boundary that we want to glue along the boundary. So we have here a manifold M, boundary dm, and on the other side we have some manifold N, dn. They have the same dimension, and we have a homeomorphism between the two boundaries. Okay, so now we can basically use the same definition as before to also define simplicial volume of a manifold with boundary, just taking relative chains. And then we can ask the following question. So if we know that the simplicial volume of these two pieces is 0, does this already imply that if we glue the two things, let's call this homeomorphism F, if we glue these two things, then we get a closed manifold, and we can ask whether this thing will also have trivial simplicial volume, right? This is a very natural question, and this will, of course, enable you to enlarge your set of examples where you can compute it. Okay, so now let's assume we want to prove that. Okay, so we start. How do we start? Well, okay, we know that these simplicial volumes here, they are 0, so we will find relative chains. Let's call it Cm here and Cn here that have very small norm. So okay, and then, yeah, well, how do we get a fundamental cycle of the whole thing? Well, we just take these two things and add them up, right? I mean, using this homeomorphism. But then, of course, there's a little problem, because, I mean, here, on the boundary pieces, they might not coincide. So we have the boundary of these chains here, but maybe if things don't work out as nicely as we want to, they might not be equal. Right? But of course we know that they have small norm, because Cm and Cn had small norm, and that they will represent the same class, maybe up to sign. Yeah? So because they are fundamental cycles of these boundaries. So what we need is, we need something that connects these two things. So we just need something that glues this. So we need a B such that the boundary of this is just like difference or sum, depending on how you choose the orientations of these two things. But now if we want to have small norm in total, then we need to control this norm of B, right? So we need a filling that's efficient to make it work. So what we see is that if the boundary of M, which is the same as the boundary of N, yeah, well, maybe let's put it like that. If the singular chain complex of this thing with real coefficients with respect to the L1 norm satisfies n minus 1 UBC, then we get a yes here. Because then we can do exactly that. And if this does not satisfy n minus 1 UBC, well, then you have to find a different strategy to do it. Okay, so it's extremely helpful to know that this thing satisfies UBC. And, well, so for example, we learned already that at least in the case of groups, that if you have an amenable group, then you always have UBC. And yeah, so this in fact also holds for spaces. So if you have a boundary manifold and the fundamental group of that thing is amenable, then you will have UBC, and then you can glue in this way. So let me just mention that, so this is really the simplest case of gluing, right? You have 0 on both sides, you want to have 0 in total. You of course can ask more generally, well, if this is some value and this is some value, will you get the sum of the two values for the glued manifold? And this is much more complicated. I mean, you have to think about a lot more things. So, but let's stick to this simple case. So you see that if you want to have gluing formula for simplicial volume, then it's good to have something like UBC. Okay, so let me move on to a different kind of problem. That's the following. So I want to talk about integral approximations of simplicial volumes. So I want to look at the following question. Maybe let's call it star. So for which, and let's assume that the manifolds are spherical to make it a reasonable question. Oriented closed connected and manifolds M with, and let's assume that this manifold has enough finite covering. So let's assume that pi 1 of M is residually finite. And then the question is whether we can compute the simplicial volume with real coefficients in the following way. Well, what could we do? We could look at all finite coverings of M. So let's say N is such a covering. And then we could look at the simplicial volume with integral coefficients. I'll just give you the definition in a second. And then normalize by the covering degree. So let's assume P is our covering. So we take all finite coverings of M. So again, so if I have a manifold, I can look at all finite coverings. On each finite covering, I can look at this integral thing and then optimize over all finite coverings where normalized by the covering degree. And of course, I mean, people that work with the rank gradient and stuff like that, or homology gradients, I mean, they recognize that this is basically a very similar thing, but for simplicial volume. So let me modify my definition above for the simplicial volume so that we can also treat this case. So let's add some coefficients. And now for what we want to do in the very end, so let me not only use constant coefficients but also twisted coefficients. So with coefficients in a normed Z gamma module A. And now what we want to do, of course, is we want to replace the real numbers everywhere by these new coefficients, right? But in order for this to make sense, we need to be able to talk about something like a fundamental cycle. So maybe the easiest thing to do is to assume that we have a map from the integers with the trivial action to A, because then we can always compare with the fundamental cycles that come from integral coefficients. So or let's assume we have a map, a gamma map from the integers to A, to our coefficient modules, then we can say what a fundamental cycle is, and then we can do the same thing. If we assumed that the module was normed, we can take the norm from A here and do the same definition. So in particular, if we have the integers, then we can just look at this number. So maybe if you look at this integral definition, it might also look more natural than the definition with real coefficients, because it's more like counting simplices, right? But well, remember these are singular cycles, so they can also get pretty wild. So it's very different from actually counting simplices in a triangulation or something. Okay, so that's the question. Okay, so why would you look at this question? So first of all, it's a very natural question. I mean, whenever you have a topological object, you can, and an invariant, you can ask, well, can you compute it from the finite coverings and some variant of the invariant on the finite covering? So, okay, it's a natural question in that sense, but it's also interesting because of the following question. So this is a long-standing open problem by Gromov. So let M be an oriented closed connected and aspherical Da-da-da. And then the question is, so, well, if the simplicial volume of this manifold is 0, does it already imply that the Euler characteristic is 0? Okay, this might look like a ridiculous claim, but so far all the examples that we know support that. And he also gives a hint on how to prove that. And how would you prove it? Well, one can compute the Euler characteristic from L to Betti numbers. So, like, one version of this would be that if this, if the usual simplicial volume is trivial, do we then have that all the L to Betti numbers of the manifold are trivial? Right? And then, okay, what's the relation to what I said above here? So if this were true, if you could compute simplicial volume by looking at finite coverings and the integral version here, then one could prove the second part, because the integral simplicial volume via Poincare duality will give you an upper bound for Betti numbers with integral coefficients. And then, for example, using the Löh approximation theorem, you would see in this case, if you take this infimum with the Betti numbers here, you get just the L to Betti numbers, and then you would get this bound. Okay, but I mean, so this question, I think, I mean, the only real foundation for this question is that the examples that one know fit with the question, but yeah, I think one shouldn't expect this to be true, right? I mean, by now we know so many really strange aspherical manifolds. It's just, I think it's just biased by what was known. Okay, so, but in this context, it's interesting to investigate this approximation question. So, let's give some partial answers. To this question star. So let's start with the good news, right? So it's true for aspherical surfaces. And in fact, this is basically, I mean, the easiest way to compute the simplicial volume of a surface is to do just that, right? I mean, you have this lower bound in terms of integration and straightening, and then you need an upper bound, and then you just construct good cycles on finite coverings of surfaces. Okay, so that's simple enough. Okay, so yeah, what's another good candidate? I mean, we had here amenable fundamental group. So let's say yes for aspherical manifolds with residually finite amenable fundamental group. And well, then again, so the proof basically also can be formulated like this. You look at suitable finite coverings, and then you find good cycles, and then you average. Okay, so this is more or less straightforward, and this is contained in a joint paper with Roberto, Cristina Pagliantini, and Roman Zaun. Okay, so that's also good. Okay, so let's see, what else have we got? Well, now, one other example here is that if you have, say, for simplicity, you have an aspherical manifold and it admits a non-trivial S1 action, then you also get vanishing of the simplicial volume, and the same thing can also be done for this approximation. So this is yes for aspherical manifolds with residually finite pi1 that admit a non-trivial S1 action. And this was proved by Daniel Fauser, who's a PhD student of mine. And I'll say something about the proof in a few minutes. And then what else have we got? Well, we could look for higher dimensional hyperbolic manifolds, right? This is very natural. So let's see. Also, it's yes for hyperbolic 3 manifolds. And, well, how do you prove that? So this is first, Christina and we showed that some other invariant that I will talk about in a second is equal to simplicial volume, and then together with Roberto and Roman, we figured out that this actually gives this approximation. Okay, but again, I will say more about this. But so the good news ends here. So the very bad news is that for higher dimensional hyperbolic manifolds, it's definitely not true. So no for hyperbolic manifolds in dimension at least 4, and this was proved by Francaviglia, Frigerio, and Martelli. Okay, so what's going on here? So I mean, it looks like if you look at this for the first time, then you might think, oh well, I mean this is easy, right? We look at finite coverings of our manifold, and the only thing that we have to do is look at somehow the geometry topology of these finite coverings, come up with good fundamental cycles, and then we are done. But it's not as simple as that. So as this example already shows, and so why does the approximation fail? In this case, it even fails uniformly. So there's a uniform gap. Why does it fail here? Well, because we know exactly how optimal cycles look like for hyperbolic manifolds. And then you can just show well, some like real geometry to figure out that this cannot happen with integral cycles. Okay, so this is like the brief idea for that. So how do we prove the positive things? So, well, I mean, especially in the case of hyperbolic 3 manifolds, it might be surprising that we didn't just do like finite coverings, look at the finite coverings, and do a smart construction. We couldn't do that. So what we do instead is the following. So we have this infimum here, and one can realize that this thing has a different description, namely, let me put it here, this is simplicial volume of M with strange coefficients. And what are the coefficients? I take the profinite completion of my group, so pi1 M hat, and well, this is a probability space, and the fundamental group acts on this probability space in a probability measure preserving way. And then I can look at bounded functions on this space with integral coefficients. And it turns out, if you look at this thing, then this gives exactly this infimum. So now we have like a dynamical description of what this approximation thing is, and this is actually what we use. So both for these for the hyperbolic 3 manifolds as well as for the non-trivial S1 actions, one needs some ergodic theory to make it work. So one uses this description from over there using these strange coefficients, and then, well, one has to figure out that for these coefficients one can do something in these situations. Okay, so yeah. Maybe let me make one more comment on the S1 actions. So in the classical case, for classical simplicial volume, this was first proved by Jano. And he gives a very geometric concrete construction, which is good for our purposes, because, well, this is something that one can translate into this strange setting. But then one also needs gluing results, like for all the intermediate steps. So we needed to figure out how to glue stuff and control these norms. So we want to know, what about gluings and this question star? And the main problem is that in this integral setting, I mean, this is all kind of integral. We always have some version of integral coefficients there. There is no good replacement for bounded cohomology, right? So there is no bounded cohomology available for this. So if you want to prove a gluing result and you want to use something like UBC, well, you can't use bounded cohomology to prove that your strange chain complex satisfies UBC. So you need a new strategy to do that. And that's what I want to explain now. So that's the third part. So I want to explain how to prove uniform boundary condition without using bounded cohomology. And I want to demonstrate this in a very simple case, and then I'll explain how to generalize. So let's look at the following proposition. So let gamma be a, and for simplicity, let's assume it's finally generated. Amenable group, and let n in n. And then, well, we already know that the chain complex satisfies n UBC, but let's prove it again. So the proof that I want to give now will not use bounded cohomology. And this proof is basically the main step in what I did together with Danya. So, okay, how does it work? Well, let's see. So we have a finitely generated amenable group. So let S be a finite generating set of gamma. And let's assume that we have a boundary in Cn. So let's see in the image of the boundary map in Cn of gamma. So say C is equal to the boundary of B, right? And now what we want to do is we want to modify B so that it has small norm in comparison with C. So the goal is improve B. Okay, so what's the first step? We first lift it to the corresponding resolution. So geometrically speaking, this would correspond to lifting everything up to the universe covering. So let's lift to C star gamma. So this is the simplicial resolution of R by R gamma modules. Okay, so how do we do that? Well, I mean, we know that this chain complex in terms of this resolution, well, how does it look like? Well, it's just Cn gamma, and then we tensor over R gamma with our coefficients, right? So, I mean, by definition, we can lift C and B to this Cn, right? So let C in Cn gamma and B tilde in Cn plus 1 gamma be lifts of C and B. And well, let's make an additional assumption. Of course, we can lift in a smart way, namely, we can lift C in such a way that the norm is not increased, right? I mean, we can just lift simplex by simplex. Okay. Okay, so now we lifted our chains, so maybe I try to draw a picture. So, well, this will be hard. Okay, so now we have a lift of C in this complex, and then we have the lift of B, and of course the boundary of B tilde will not be exactly C tilde, because these are just some lifts. I mean, things could go wrong, right? I mean, this is only that the boundary of B is C, it only holds in the quotient. So we don't know actually what the boundary of B tilde is. Well, it's something related to C tilde, but there isn't more. Okay, so that's the first step. Then what's the second step? Or yeah, that was the 0th step. So what's the first step? Is now we want to have some group actions going on. So, and that's now good because on this resolution, I mean, that's the whole point, we have gamma acting. So we can let gamma act, and well, what do we want to let act on our chains? Well, our group is amenable, so we will use Fellner sets. So second step is translation by Fellner sets. So yeah, let Fk with k and n be a Fellner sequence for gamma. So this exists because gamma is amenable. And well, what does it mean that it is a Fellner sequence? It means that if you look at the S boundary of F and you count the number of elements in comparison with the number of elements in your set, then this tends to 0 for k going to infinity. So this just means these sets have small boundary, at least in the limit. Okay, so that's the Fellner sequence. And then now we let these things act. Okay, so for k and n, we define the following. Namely, we look at, let's call it k tilde. And what is it? Well, we can just take all the gamma in the k Fellner set and let them act on B tilde. Right? This gives you something in Cn plus 1 of gamma. So I'll try to draw a picture. So we have C tilde here and B tilde here, and now you let your group act, and then I need more colors. So now you let your elements from the Fellner set act, and then you get something like this. So the thing here will be something like Fk times C tilde, and the whole thing will be Bk tilde. Okay, so we have that. And now what do we do in the next step? Now we can look at the boundary of these sets, and then we can try to fill them more efficiently than before. So we look at efficient fillings of the boundary of Bk tilde. Okay, so I mean, this is all of this happens in Cn plus 1 gamma or Cn gamma, whatever you want. So this is contractible, right? Whenever I have a cycle, I can fill it. But this is a special chain complex. I mean, this is the simplicial resolution. So we can know that we can fill very cheaply just by coning off. So if we have this boundary of Bk tilde, let's see, that's this purple thing here, right? Now we can try to fill that using a cone construction. Okay, so use cones to find, I don't know, I'm running out of letters, capital B K tilde with the property, well, that the boundary of this thing is just the same as the boundary of BK tilde, which is a cycle, so I can fill it. And the additional property now that I want to have is that the norm of capital BK tilde is less or equal than the norm of the thing that we fill. And as I said, you can do this because you can just use the coning construction. So this will be this thing. Okay. So now, what did we gain? Well, we can control the size of the boundary of BK tilde, because this is not just any chain, but we got it from B tilde by translation of a Fellner set. So this is the size of this boundary is controlled by, well, some constant that will also depend on B, but that doesn't really matter, times the boundary size of the boundary of the Fellner set that we used, plus well, roughly the size of the Fellner set itself times the norm of C tilde. And this is, of course, by construction bounded by the norm of C. Okay, so this is, I mean, if you look at this picture, so why is this true? Well, we know that in the quotient, if we divide out by all the gammas, right, then we know that the boundary of B is C. So, well, we know that, you know, if we basically, if we would take all of the fk in the limit, then the boundary would be 0. And, well, of course, this is not true in the finite steps, but the thing that controls the size of what remains is basically, well, we have these terms that do not belong to the boundary of, or do not belong to C tilde. Well, that's basically, I mean, the thing that remains is just the boundary of f, because everything else will cancel. And, well, then there's a thing that you cannot get rid of, and that's the translates of C tilde, and that's this term. Okay, so that's what we have. And now we are almost done. The only thing that we are left to do is to just project everything back down again. So this is the quotient snap. That's the last step. Let me put it here. Okay, so there are two quotients that we will take at the same time. Namely, one is the quotient that we project down to the chain complex of gamma, to the chain complex that we actually want to have. And the other one is that we also want to divide by the number of elements in fk. So we consider the chain bk, that is defined as 1 over fk times the projection of bk tilde to the coinvariance, right? And this gives you a chain on gamma with real coefficients by construction. So what do we have? By construction, well, the boundary of bk, well, it's basically the projection of the boundary of capital BK tilde, but by construction, the boundary of capital BK tilde is just the boundary of BK tilde, and that's basically just taking fk times the boundary of B tilde, and, well, if we project it down, this is the bound, and this is just f, so sorry, C, so this is just C. That's the thing that we wanted to have, right? And what do we know about the norm? well, the norm is bounded from above by 1 over the number of elements in our Fellner set, well, times the norm of capital BK tilde. But we have an estimate for this norm, so there is some constant, and then we have the boundary of the Fellner set divided by this Fellner set plus, well, we have this term coming from C times the size of the Fellner set, but we divide by the size of the Fellner set, so that's the thing that we are left with, just the norm of C. And of course this first term here, because fk is a Fellner sequence, this goes to 0 if k goes to infinity. So if we take k large enough, then we will find a very good filling of C. And that's what we wanted to do. Okay. So yeah, a few comments on this. So first of all, this is very similar to what we did with Roman and Roberto to calculate these integral versions of simplicial volumes for manifolds with amenable fundamental groups. So this is just like the UBC version of that proof, so to say. So that's one thing. And then what did we gain? Well, now this is still with real coefficients, right? But this proof has the advantage that, well, basically, I mean, for a large part of the proof, we were not concerned about coefficients at all. I mean, basically, the only situation where we really used that we have real coefficients is this step here, right? Where we divide it by the number of elements in the Fellner sets. But now, well, if your situation is good enough, you can replace this by some other mechanism. So for example, if you're in the situation of having L-infinity functions on some probability space on which the fundamental group acts nicely enough, then yeah, you can replace this division by division in the measure space. And then you, for example, you get the following result. So a similar proof gives the following, that C star of now just some free abelian group with coefficients in L infinity x z, where now x is a space on which zb acts by probability measure preserving transformations, and this should be good enough, so this should be essentially free, that this gives, this satisfies NUBC. And then you can use this to prove some gluing results also for these for this integral approximation of simplicial volume, provided that you have strong enough vanishing on both sides, again expressed in terms of some ergodic theoretic properties. So that's why we're interested in this different proof for UBC, because this is a proof that you can generalize to these integral settings. Okay, thank you very much.
What about groups that have NUBC for every n but are not amenable and not known to be amenable?
They exist. So, okay. So as we have seen, so if you have a group that has trivial bounded cohomology, then you have UBC in every degree. And you can construct loads of these groups. Okay, but all of these groups will be, I mean, so the known constructions, they will give you like strange groups.
I just make a little announcement that tomorrow there will be, for possibly of some of you interested, a seminar from the operator algebra part, which is going to be enough interest for some of you. There was some group action on trees of totally disconnected groups, and I think they move it half an hour earlier so as not to overlap Jing's talk. So it will be at 1:30 at 1:30 in the afternoon, and it will not be in this room. So just for you to know. And we thank Clara again.